So today we're going to talk about sets. This is important, especially for those of you who are in computer science, eventually going to write queries using database, language, structured query language. In SQL, for example, you're working with tables and you're finding the union of tables or finding the intersection between data columns in different tables, or you're finding difference and more operations in SQL for tables. Tables are basically sets. In this chapter, we're going to talk about the relation between two sets, three sets, and more, how to analyze sets, what's the relation between sets, and how to prove those important properties in between sets. Set theory. So let us start by the basic definition of set theory. Elements in set theory are sets. Definition of a set. A set is a collection of numbers, objects, and so on. So you can add any entity to a set. We denote a set by curly brackets. We assign, for example, capital letters like S, A, B, C to sets. So we talked about the elements of set or member of set in chapter 1. So let us talk about two sets. Let X and Y be two sets. When you have two sets, you might have some relation between them or no relation. The first case, case 1, is that X might be a subset of Y. So X is a subset of Y. The second case, case 2, is that Y might be a subset of X. Well, Y is a subset of X. Case 3, they might have no relation. X intersection with Y, it might be empty. No relation at all. So if you want to use Venn diagram says, in this case, Y is the bigger set and X is the smaller set. X is included in Y. In this case, however, X is the bigger set, the larger set, and Y is included in X. Here we go. In this case, they have no relation. Y is here, X is here. They might have some intersection somewhere. So we can add more cases. X and Y might have some elements in common. So the intersection might not be empty. You have your Y, and when you take the intersection between X and Y, there are some elements in common between them. So you can write X intersection with Y is non-empty. So remember that when we say X is a subset of Y, it means that if you take any random element, in set X, any random element here, that element belongs to Y. So if I take any random element in X, that element belongs to Y as well. We say that Y is a subset of X. It means that if I take a random element in Y, like B, that element belongs to X as well. When we say the intersection is empty or we have disjoint set, it means that if I take an element here, that element cannot be in X, and if I take an element in X, that element cannot be in Y. When there are some elements in the intersection between X and Y, you can find some elements that belong to X and belong to Y at the same time. So suppose you have an element like C. C belongs to X, and at the same time, C belongs to Y. But you might have some elements in Y that are not in X, and some elements in X that are not in Y. Okay, very well. When do we say two sets are equal to each other? Two sets are equal if and only if, suppose you have two sets like A, X and Y, if and only if X is a subset of Y and at the same time Y is a subset of X. X is a subset of Y and Y is a subset of X, then for sure you can say that, hey, these two sets are equal to each other. X is equal to Y. So to prove that two sets are equal to each other, you have to show that. If you take any random element in X, that random element belongs to Y. If you take any random element in Y, that random element must be in X. From X to Y and from Y to X. Both ways. Let's go over some examples. Example. Suppose A is given to you as the set, including just one member, and B is another set which includes 1, comma, a set including 1. Very well, question says A. Is A a subset of B? And B, is A a proper subset of B? So take a look at these two sets. If I take any random element in A, if I take any random element, I'm talking about an element which is a member of set A. It only has one member. 1 belongs to A. Does 1 belong to B as well? Yes. 1 belongs to B as well. So the answer is yes. A in general is a subset of B. Now we want to investigate that in more detail. Since you have finite numbers of elements, it's possible for us to check to see if A is absolutely a subset of B. There is no possibility of equality. Okay, can we investigate that? Think about it. Set A has cardinality equal to 1. Set B has cardinality equals to 2. there is no way these two sets be equal to each other. So you can write, since the cardinality of set A is equal to 1, the number of elements in set A is equal to 1, and the cardinality of set B is equal to 2. So for sure you can say that A is a proper subset of B. So A is a proper subset of B. So this is true. Example for you. Suppose you have two sets defined this way. Let A is equal to the set of all integers M belongs to Z such that M is equal to, M can be written as 6 times R plus 12, and R is an integer. B is defined as the set of all integers N such that N is equal to 3S and S is some integers. Very well. What's the relation between A and B? Is A a subset of B? Is B a subset of A? Are they equal to each other? Okay. To investigate relation between A and B, we need to check to see if A is a subset of B, if B is a subset of A. If these two are both true, we can say that, hey, these two sets are equal to each other. If the member of A is not in B, member of B is not in A, then they are disjoint. They have nothing in common. If we can find a couple of numbers, a couple of values belonging to A and belonging to B, we can say that, hey, there are some elements that are in the intersection of these two sets. Okay, let's begin. We're going to take a random element in A and check to see if that random element is in B or not. So let's write this here with a little bit more space. Let us take a random element in A. For example, M, which is defined as 6R plus 12. And R is some integers. Check to see if M belongs to B or not. This is our goal. We want to check to see if M is a member of B. Okay, take a look at the members of B. All of them are multiples of 3. All members in B are multiple of 3. You might say, hey, if I factor out 3 here, my M is going to be 3 times 2R plus 4. I can define this integer because this guy says S is just some integers. So you can write this as 3S. M can be written as 3 times some integers. So M belongs to B. We just proved that A is a subset of How about B is a subset of A or not? Let's check to see. Let us take a random element in B, like n equals to 3s or s in Z. Check to see if n is in A or not. Okay, perfect. Elements in B are 3 times s. 3 times s. If I set this equal to, for example, one of the members in A, like 6r plus 12, what do I get? I get this value. If I just bring this guy to the other side, I get 3s minus 6r equals to 12. Then it says if I factor out 3s minus 2r is equal to 12, and s minus 2r is equal to 4. Okay. Then what does it give me? I'm looking for some r values in Z such that 6r plus 12 can be written as 3 times s. Take a look at this. Here I get 2r equals to s minus 4, or r is equal to s divided by 2 minus 2. Very well. You might say, hey, I don't know how to analyze this. What's the meaning of that? S is an integer. Think about it. S is an integer. What are integers? 0, plus minus 1, plus minus 2, plus minus 3. So if S is plus minus 1, you get a fraction here. For example, a half minus 2, it gives you negative a half. It results in R to be a fraction, but R cannot be a fraction. R must be an integer. It doesn't satisfy for all S values. So B is not a subset of A. A is a subset of B. Perfect. Another example for you. This example says, what's the relation between these two sets? Our first set A is given to us as the set of all integers such that M is equal to 2A for some A integers. So M is equal to even numbers. And B is equal to the set of all integers n in Z such that n is 2B minus 2 for some integers. Okay, what's the relation between these two? Is A a subset of B? Is B a subset of A? Think about it this way. This is set A. A is the set of all even values. Take a look at B. B can be written as the set of all integers such that n is equal to 2 times B minus 1 for some integers. Okay, B minus 1 is just an integer. If I rewrite this set as n belongs to Z, such that n is equal to 2c, c is an integer, then what's the difference between A and B? B is also the set of all even values. So what's the relation between A and B? They are equal to each other. So, what is our goal? Our goal is to take a set or two sets or more and combine them together, construct a new set. This is our job. So this is our goal. To create a new set. Okay, perfect. Let's see. So, when you're creating a new set, first of all, you need to restrict yourself to the largest set that we call the universal set. To create a new set, we need to limit ourselves to the largest set. This largest set is called the universal set. So denoted by U or universal set. In set theory, when we're talking about this universal set, we usually denote this guy by a rectangular shape, and we say that, hey, this is our largest set possible, or the universal set. Then we say that, hey, the rest of the objects, the rest of the sets are inside this largest set. A is here, B is here, C is here, D might be here, E is here, F is here, and the rest of the sets. Okay, so keep that in mind. We need a largest set possible to be able to create some new sets inside that set. The very first one is union between two sets. Suppose you have two sets, like A and B. So let A and B be two sets. Their union is denoted by A union. It's different from that universal set. This is the union. Union between two sets. This union is a new set. It's defined this way. We define it as the set of, this is a new set, so we use set notation, the set of all x values such that x is in the first set or x is in the second set. So either to the first one or second one or both of them. X belongs to A or to the both. That's how we define the union between two sets. How do we denote that? By A union B. How do we visualize that? By using the Venn diagram. So here you have your universal set, in that universal set, you have two sets, like A and B. So this is my universal set. A union B. Let me use a different color so you don't confuse that. This is A union A union. The next operation, intersection. So intersection between two sets. We're working with two sets. Let A and B be two sets. Their intersection denoted by A upside down union. So upside down union, and it's defined this way. This is the intersection. Slip away. The intersection, A intersection B, is equal to the set of all x values such that x is in A and x is in B. Union or intersection and union or intersection and. Recall what we talked about in chapter 1, logical connectors, conjunction, disjunction. We're going to use those when we're interpreting the statements involving sets. Okay, how do we represent the intersection? We have our universal set. We have two sets, A and B. We just look forward to find all common elements between them. A intersection B. This is A intersection. Here we go. A. Next, we're talking about the difference between two sets. Before talking about the difference between two sets, let's talk about a set complement. Set complements. So let A be a set let A be a set. Its complement, it's defined this way. First of all, we denote the complement of A by, if you open different discrete math book, you might see these notations. A prime or A bar or AC. These are all notations for complement of a set. Now AC. So this is the complement of the set denoted by A prime or A bar or AC, and it's defined this way. A complement is the set of all values such that those values are in the universal set but not in A. X is not in A. A complement, all elements that are not in A. So if you have set A complement is going to be all of these elements outside set A. This is A Everything that is in U, but not in A. And finally, we're going to use the set complement. And we denote this guy, I forgot to write it down, U minus A as well, and talk about the set difference between two sets. Set difference. Okay, let A and B be two sets. A minus B is the set difference, the difference between A and B is denoted by A minus B. So set difference, the difference between A and B, A minus B. And it's defined as all the values such that they are in A, they are in the first set, not in the second set. X is in A and X is not in B. A minus B, the set of all X values such that X is in the first set, but not in the second set. Very well. Okay, now you have your universal set. We can use Venn diagram to actually visualize it. This is your universal set. You have A, you have B, all elements that are in A, not in B. So you have to exclude B. So we're just going to shade this part, have nothing to do with set B. This is A minus So this is our goal, to create a new set by using these operations between sets and
I have a question.
Perfect. So what's next? We're going to talk about partition of a set. Definition of partition of a set. First of all, suppose you have a set. Let A be a set. Then we consider some subsets of set A, and there are finite numbers of them. Let A sub 1, A sub 2, and the rest of them, A sub 1, A sub 2, A sub 3, and the rest of them are all subsets of A. We say that this collection of subsets, A sub 1, A sub 2, A sub 3, and so on, form a partition of A if they satisfy the following condition. First of all, they are mutually disjoint. AI intersection AJ is empty. So if you take two of them, note that I is not equal to J. If you take two sets that are different from each other, they have nothing in common. Mutually disjoint. you take their union, the union is equal to set A. A is equal to A1 union A2 union the rest of the sets. In this case, we say that, hey, this collection of subsets actually form a partition for set A. So how do we visualize that? We have a big set, a large set, like set A, and we have some subsets. They are mutually disjoint, nothing in common between them. We divide up set A into smaller pieces. A sub 1, A sub 2, A sub 3, A sub 4, A sub 5, and the rest of it. If you take the union is equal to A, and they are mutually disjoint. And note that your AIs are all non-empty. So they are not equal to empty. Not empty. Let's take a look at one example. This example tells us, suppose you have a set like A. This set is defined as 1, 2, 3, 4, 5, and 6. So the cardinality of this set is equal to 6. Then you have A sub 1, which is defined as sets including 1 and 2. A sub 2 is the set including 3 and 4. A sub 3 is a subset of A including 5 and 6. Then question says, do you have a partition for A? We have a partition. So this case is not very hard to see. First of all, you need to check to see if they are mutually disjoint or not. Then you need to check to see if you take the union is equal to set A or not. So for A1, A2, and A3 to form a partition for A, we need to check 2 conditions. Actually, we need to check 3 conditions. Each one of these must be non-empty, but they are non-empty, so we're not worried about that. We need to check the first condition. A1 intersection A2 is empty. A1 intersection A3 is empty. A2 intersection A3 is empty. This is the first condition. The second condition, A is equal to A1 union A2 union A3. So let us put question marks next to it and check each of these conditions. Perfect. So what's the intersection between A1 and A2? There is no intersection between 1 and 2, 3 and 4. This is empty. So let's erase the question mark. A1 and A3, 1 and 2, intersection 5 and 6. Do we see any common elements between them? Of course not. Empty. A2, A3, 3 and 4, intersection 5 and 6. Well, is it empty? Of course. No element is in common between them. So the first condition is met. Second condition. But if I take the union of all of these elements, A is 1, 2, 3, 4, 5, 6 on the left-hand side. 1, 2, 3, 4, 5, 6. This is my A. And on the right-hand side, I need to take the union of these three sets. So since it's union, we have to list all of these members without repetition. 1 and 2. 3 and 4. 5 and 6. Are these two equal to each other? Of course. So the answer is yes. Our next example is more interesting. Example. Okay, perfect. Now suppose you have Z as the set of all integers. Let Z be the set of all integers. Okay, we're going to define the subsets this way. Suppose T sub 0 is the set of all integers such that n is equal to 3k for some integers k. Multiples of k, or you can say that it is 3k plus 0. Quotient remainder theorem. T sub 1 is the set of all integers such that n is equal to 3k plus 1. The remainder is equal to 1 for some k integers. T sub 2 is the set of all integers such that n is 3k plus 2. The remainder is equal to 2. K belongs to Z. Do we have a partition? Okay. Take a look at this. What are the elements in T sub 0? What are the elements in T sub 1? What are the elements in T sub 2? Two conditions. First of all, they must be mutually disjoint. You need to check to see if T sub 0 intersection T sub 1 is empty. T sub 0 intersection T sub 2 is empty. You need to check to see if the intersection between T sub 1 and T sub 2 is also empty. So let's put question mark on top of it and erase that part of the board. We need more space. Perfect. This is our first condition. The second condition, we need to show that the union of these three sets is actually the same as Z itself. T sub 0, T sub 1, T sub 2 forms a partition for Z. Okay, so what is T sub 0? T sub 0 is the set of all integers such that n is equal to 3k plus 0. So n is 3k. It means that 3 divides n. That's the meaning of that. That's how we define it. Okay, what are those values? What are those numbers? First of all, the very first value is 0. K is equal to 0, N is equal to 0. K is equal to plus minus 1, N is plus minus 3. K is equal to plus minus 2, plus minus 6. K is equal to plus minus 3, plus minus 9, plus minus 12, and the rest of them. All of them are multiples of 3, or 3 divides them. What are this case here? It says, hey, N can be written as 3 times K, and when you do the division between N and 3, the remainder is equal to 1. So that's the meaning of that. When we divide N by 3, the remainder is 1. What are those values? Okay, let's plug in some of K values and list some of these elements in the second set. If K is equal to 0, N is equal to 1. If K is equal to 1, we get 4. If K is equal to negative 1, we get negative 2. If K is equal to 2, we get 7. If K is equal to negative 2, we get minus 5. And the rest of the terms. Okay, do you see any intersection between T sub 0 and T sub 1? These are all multiples of 3, and these are these numbers here. 1, 4, negative 2, 7, negative 5, and the rest of them. As you can see, the intersection between T sub 0 and T sub 1 is empty. Okay, what about T sub 2? What is T sub 2? T sub 2 is the collection of all integers. When you divide them by 3, the remainder is equal to 2. So when we divide N by 3, the remainder is 2. What are those numbers? Okay, let's find some of them. If K is equal to 0, N is equal to 2. So this is 2. If K is equal to 1, we get 5. If K is equal to negative 1, we get 1. Let's see, 3K, we have negative 1. Very good. Then if you plug in K is equal to 2, we get 8. When K is equal to negative 2, we get negative 4. And the rest of these values. Perfect. So, do we have any intersection between T sub 0 and T sub 2? Of course not. The intersection is empty. What about T sub 1 and T sub 2? T sub 1 and T sub 2. Here you have 1, here you have negative 1, here you have 2, here you have negative 2. 4, negative 4. So it seems like you get the opposite numbers. The intersection is empty. The first condition is met. We're happy about our first condition. What about the second condition? The second condition says Z is equal to T sub 0 union T sub 1, T sub 2. Is this true? Okay, we know what Z is. 0 plus minus 1 plus minus 2 plus minus 3. From negative to positive. How about if I find the union between T sub 0, T sub 1, and T sub 2? Okay, this guy has all the multiples of 3. It also includes 0. This guy has negative 2. This guy has positive 2. And I already know that there is no intersection between them. So whatever is left that is not multiple of 3 is either here or here. Very well. So for sure you can say that, hey, this is equal to the union of 0 plus minus 3 plus minus 6 and the rest of them union with 1, 4, negative 2, the rest of them union with 2, 5, negative 1, and so this condition is also met, and the answer is yes, we have a partition. Well, you might say, hey, you used quotient remainder theorem for 3. What if I use quotient remainder theorem for 2? Quotient remainder theorem for 4? For 5? Of course, you can create a lot of different partitions for Z. Note that Z can be partitioned using even odd numbers. 2k plus 1. In this case, we have 2 partitions. Z can be partitioned using, so we just showed 3, so let's write down 3k plus 1, 3k plus 2. This is Z. You can partition Z using 4. Another partition for you. Why not? Z can be partitioned 4k plus 1, 4k plus 2, and 4k plus 3. These numbers have nothing in common. And you can continue this process. You can use your 5, your 6, your 7, and the rest of the numbers. You get more partitions. Perfect. So now we just talked about some examples. We're going to see how we can use mathematical proof to prove relations between sets. Set theory, mathematical proof. Perfect. So we have some nice theorems. Here. The first theorem says, suppose you have 2 sets. Let A and B be 2 sets. Okay, we have the following. A, if you take the intersection between A and B, it's going to be a subset of A. If you take the intersection between A and B, it's going to be a subset of B. Then we have the following. This is related to the intersection. We're going to talk about the union. A is a subset of A union B. B is a subset of A union B. And the last property is transitive property. This property tells us that if A, B, C are sets, if A is included in B and B is included in C, then for sure you can say that A is included in C. Okay, here we have inclusion of intersection, and here you have inclusion of union. But how do we prove this? To prove that A intersection B is a subset of A, we need to show that any random element in A intersection B is also in A. Any random element in A intersection B is also in A. Okay, so let us take a random element in A intersection B. X belongs to A intersection B. What's the meaning of that? By definition, of the intersection, this X belongs to A, X belongs to A, and X belongs to B. So X is in A, yes. Since X belongs to A, we are done. What about this guy here? The same process, the same argument. We need to show that any element, random element, in A intersection B is also in B. How do we show that? To show that, you need to take a random element in A intersection B. Suppose X is a member of this intersection. By definition of intersection, so we know that this is just a direct proof by definition. By definition of A intersection B, X is in A and X is in B. Okay, do you see that X is in B? Of course. So since X is in B, we are belongs to B. Good. How do we prove this? A is a subset of A union with any other set. This is very trivial. You need to show that for any element, any random element in A, that element is in A union B. But it is obvious by using the definition of A union B, the proof is obvious. The same for part B. You need to show that, this is the logic behind it. You need to show that for any random element in B, that element is in A union B. B union with any other set. But this is obvious. Why is obvious? You're taking an element in B and you're showing that that element still belongs to B union with some other sets. Of course it's true. By using the definition of A union B, it is obvious. What about the transitive property? If A is a subset of B, B is a subset of C, then A is a subset of C. So, to prove that A is a subset of C, we need to show that any random element, any element in A is also in C. But how do we prove that? How do we show that? Let me put these question marks here. Okay, let us start. We need to take a random element in A. Let us take X in A. We know that A is in B. Since A is a subset of B, X belongs to B as well. At the same time, B is a subset of C. So X must be in C. Are we done? Yes, we're done. So we are done with our proof.